There are several things I want to do in this video. The first is to walk you through the Kinetics simulator spreadsheet that I've uploaded. This spreadsheet will allow you to practice a bunch of the skills you'll need on midterm exam 2. Second, I'll talk you through some of the basics of using Microsoft Excel in general. I'm going to do that in the context of solving specific Kinetics-related problems, but they're generally applicable to all sorts of problems beyond this specific spreadsheet. And third, I will talk you through some of the types of analyses that these simulations can feed into. There's a lot to talk about, so let's dive in. And I recommend having the spreadsheet up and following along yourself throughout the video. The first thing to notice when you open up the spreadsheet is that there are 3 tabs located on the bottom that let you move among different parts of the simulator. In the main tab, labeled Experiment Setup, you will enter parameters that define the experiment you want to run, like temperature, the initial concentrations for the reactant species, how frequently you'll be taking data points, how long to take data for, those sorts of things. The simulated data itself is shown, as well as a graph of the data. The second tab, labeled Rate Law, is where you can set up what rate law you want to be simulated. You can specify the reaction order and stoichiometry for each reactant, product, and catalyst or inhibitor, and the frequency factor and activation energy for the reaction as a whole. In the exam spreadsheet, you will not have access to this tab, because I will set up the rate law myself that you will have to determine based on experiments you simulate on the first tab. But in this practice spreadsheet, I want you to be able to set up different scenarios for you to practice. In the final tab labeled Runge-Kutta, this is where the simulation actually happens. Don't worry about what Runge-Kutta actually means. You should never even have to look at this one, and I will also prevent access to this tab in the exam version. Just leave it alone. The general design philosophy for this spreadsheet is that the things you can change are in yellow. If it's not in yellow, don't change it, because you could screw something up in the internal calculations. Okay, so let's now look at what our first kinetic model is. We're going to start simple. We've got 6 possible species labeled A through F, and for each we can assign an order and a stoichiometry. Let's talk about stoichiometry first. The number that we put in this column is the stoichiometric coefficient in the balanced chemical equation, but with a negative sign if it's a reactant. So if, for example, we want to have 2a plus b goes to c plus 2d, we would enter -2, -1, let's type it correctly, -1, 1, and 2. Notice down at the bottom we see the resulting equation, so we can check to make sure we've done it right. And if we click back over to the Experiment Setup tab, we can see the reaction up here at the top. But our first example is going to be an easier one. We're just going to have A go to B. Next, we need to look at reaction orders. The way it's set up now, the calculations won't work right if you give reaction orders to products. That is because if you imagine starting the reaction without any product, you are raising 0, the initial concentration, to a power, and then the rate becomes 0. What's going on here is at the very early times of the reaction, the approximations we make to generate a rate law for an overall reaction, like the steady state approximation, don't fully work. So within the context of this spreadsheet, just know to not give the products a reaction order. You can see down at the bottom the resulting rate law, just to make sure you have it set up the way you want to. We'll leave it at first order in A for the moment. And then on the right, we have the rate coefficient information. The frequency factor and the activation energy are used to determine the rate constant at the temperature that is specified in the Experimental Setup tab here. This is the rate constant that's determined. The noise level here is the random jitter in the data that simulates measurement uncertainty. Again, remember that this is set up so that you can design practice problems yourself. In the exam version, you won't have access to this page, so I will have set all of these parameters, and it will be your job to figure out the rate law. Moving back to the experimental setup, change this a little bit. Moving back to the experimental setup, we see that the things you have control over are temperature, the initial concentrations of all the species. We can specify which species concentration we are monitoring. If I select a product instead of a reactant, we can see the appearance of the product instead of the disappearance of the reactant. If we change the initial concentration of the reactant, we can see our signal change. The signal gets higher. If we raise the temperature, you can see the reaction getting faster. Okay, now let's look at how to capture this data and analyze it. The first thing we want to do is to make a new Excel workbook to put the data that we're going to analyze in. File, New, blank workbook. We now have a new workbook. Okay. We should label our columns so we can keep track of what we're doing. I usually leave a couple of blank rows at the top in case I need to put any other information up there. And with the labels, it's generally good to put the units in parentheses so you can be sure to keep track of them during your analysis. If you want to format it, you can do so, and you might want to add identifying information up at the top. Now let's go back to the simulation spreadsheet and get our data. The easiest way to do that is to use some named ranges that I have set up. I've called the time points capital X and the concentrations of the monitored species capital Y. So if you click in this box right here and type capital X, comma, capital Y, and hit enter, the full data range will be selected. Control C to copy, switch to your new spreadsheet, place the cursor in the upper left cell where you want to paste, then right-click and select Paste Values option, because you don't want the formulas that do the calculations copied over, you just want the numbers. And you now have the data. Alright, let's now learn enough Excel to do the calculations you need to do. There are three types of cell contents you need to know about. The first is a number, just like you have here. Notice that the number that is displayed in the cell itself has fewer significant digits shown than the number up here in the formula bar. Numbers can be formatted in a lot of different ways, which we aren't going to go into for now. The second type of cell is a label, such as this. Labels can't participate in the calculations we're doing. Notice that this cell right here is also a label because it contains an M in addition to the number. That M means that this is considered to be a string of characters, not a number that can participate in the calculations. So if you want to be able to use this as part of a calculation, you would probably want to do 0.002, and then in the next cell say that's molar. Finally, the third kind of cell is a formula. This is where Excel can save you so much time and effort. Let's suppose that the first thing we want to do is to determine reaction order. So we want to plot concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. So we'll set up column headings for these. Okay, we'll start with the natural log calculation. We start a formula by typing an equals sign. Think of this as signaling to Excel that the cell value will end up equaling what you put after the equals sign. If you type a formula with numbers, it will do the calculation. You use an asterisk to mean multiplication, and you use a caret to mean exponentiation. That lets you use Excel as a fancy calculator. But the real power is in having Excel do calculations on other cells. Let's type an equals sign, LN, open parentheses, and then press the left arrow key. Notice what happens. The cursor has moved to the cell next to it. And if we look up at the formula bar, we see it says equals LN parentheses B5. B5 is a cell reference indicating which cell to take the number from, meaning column B, row 5. We close our parentheses, hit enter, and see the result of our calculation. Now let's put a cursor on that cell. Notice that while the cell itself shows the result of the calculation, the formula bar up here shows the actual contents of the cell is the formula, not the number. That lets Excel update the value if we change the number, like this. Now, of course, we don't want to screw up our data, so I'm going to hit Control-Z to undo that change. Okay, next let's copy and paste our formula down a row. Control-C to copy, Control-V to paste. Now look at what's happened. In the top cell, its formula is the natural log of cell B5. In the bottom cell, it's the natural log of cell B6. Excel is smart enough to recognize that when you are copying and pasting a formula, it needs to increment the row count within the formula when the place you are pasting it is on the next row. You can do the same thing for columns too. Take a look at this. So if we look here, we have natural log of B7, B8, B9, and if we go over, natural log of C9, D9, and so on. Now, that's not what we're wanting to do with those columns, so I'm going to undo again, but there may certainly be times when you're using Excel when you want to increment the column as well. Let's now look at our 1 over A column. You should be able to tell what to do here. So if you're following along in your own Excel spreadsheet, you might want to pause the video and try it yourself. And here we go, equals 1 over cell B5. Hit enter, and we have our answer. And just like before, let's copy it down 1. Now, we would like to copy this down for the entire data set, and let's do both formulas at once. First, we'll select both formulas. We can do that by clicking and dragging. We can do that by clicking on the first cell and shift-clicking on the second cell. A shift-click will select the two cells and everything in between. We can do it by clicking on the first cell and control-clicking on the second cell. Control-click, unlike shift-click, does not select the stuff in between. That will be important if we need to select a cell here and a cell here, but not what is in between. We can do this also by clicking on the first cell, holding down the Shift key, and pressing the right arrow key. Holding the Shift key while you press an arrow extends the selected region in the direction of the arrow movement. However you decide to do the selection, press Control-C to copy. Notice the traveling dashed border indicating that there is something copied. Now I'm going to select a range of rows in the natural log of A column. Use any of the methods I mentioned before. Right now I'm click dragging, and I hit Control-V to paste. Notice what happened. It took the region I copied and repeated it once for each row. And it recognized that because I had selected two cells next to each other, that the paste would have to extend to the next column over. Pretty slick, huh? Okay, one more Excel navigation trick. I'm going to place my cursor in this cell. Now I'm going to hit the End key followed by the down arrow. When I do that, the cursor travels in the direction of the arrow until there is a change in the cells. If I started in an empty cell, it will travel to the last contiguous empty cell in that direction. If I started in a cell that has contents, as I just did this time, it will travel to the last contiguous filled cell in that direction. This is a really convenient way to traverse long regions of a spreadsheet. Let's look at how we can use it. Select the two formulas we want to copy by selecting whichever method you want. Control-C to copy. Click somewhere in our data, End followed by down arrow, and suddenly 1,000 cells down at the last data point. Now we can click over here where we want to paste, hold down the Shift key, and press End followed by the up arrow, and that brings us back to where we were copying from, selecting all of the cells in between. Still holding the Shift key, press down arrow, and we're ready to paste. Control-V. And magic. We have all of our calculations done. End up takes us back to the top, and we're ready to see what kind of kinetics we have. To do this, we need to make 3 plots, one to test 0th order, one to test 1st order, and one to test 2nd order. To make a plot, we have to select the x-axis data and the y-axis data. We'll start with the 0th order case, where we just plot the concentration versus time. Click in a corner of the range, Shift End down, Shift right, and we have our data selected. But if we do the Insert Chart command down here, our chart will be down in row 990 something. So I'm going to click and drag back up to the top, And now insert scatter chart. There are lots of kinds of charts, but in science you'll almost always want scatter charts, where you are specifically specifying the x-coordinates of your data points. Most of the other types of charts in Excel don't do that, and so are largely useless to science. Click it, and it's inserted. Just to keep things straight, we can label it. And because we can look at this and see that it's not a straight line, we know that we do not have a 0th order reaction. Okay, next plot, testing first order. Again, click on the first time point, Shift End down. Now release the Shift key, press the Control key, and click on the bottom of the natural log column. That selects the natural log cell without selecting the straight concentration cell in between. Switch back to Shift, and Shift End up to bring us back to the top. Press the, still holding the Shift key, press the down arrow to deselect the column heading, and we're ready to insert the next chart. And that looks quite linear. Now there are some bad data points because the noise is getting some of the data points negative, and natural log of a negative number is not defined. So we'll have to deal with that somehow in a bit. Also, the noise is getting bigger as we approach later times. We'll tackle that later as well. Let's finish the order analysis. Before we forget, we'll label this and move it up here. And our last plot is the second order check. We do the same thing. You should know how to do this by now. Click, End up, one down, insert, chart, scatter. And this one is hard to see because we're so freaking zoomed out because of the noise data down here. All right, so what can we do about that? Well, if we look up here, we can see that the data is pretty good up to about 300, maybe up to 400, but after that, it's starting to spread quite a bit. So let us come down, scroll down some, and at about 300, we're just gonna cut off our data. Come down here, delete the data, head back up to the top, and now we can see very clearly that our second order test plot is definitely nonlinear. So we have confirmation that our reaction is in fact first order. All right, time to find the slope so we can find the rate constant. This is the plot that we're going to care about. I'm going to scroll up. Now that I know what it is, I'm going to get rid of the two we don't need. I'm going to move this over. And the plus sign here means to add a chart element. What we are going to do is add a trend line and select linear. Now, there is a trend line on here. Unfortunately, it is colored the same as the data point, so you can't see it. So if I click right in the middle, come over here and change the color of the trend line, and then change it from dotted to straight, we can see the linear fit that has been put in place. If we select here on the trend line, we can go down, display equation on chart, and we can see that we now have our equation for the line. Maybe we want more significant digits. We can come over here, select the label options, identify this as a number, and give ourselves some more decimal points. And we now have our slope. So this now tells us that our rate constant is 0.00917. Let's see how close we are. Come back to our simulator, come back to our rate law, 0.00918. That's pretty darn close. That's definitely within experimental error. Okay, so now you know how to analyze a set of data in Excel for simple 0th, 1st, or 2nd order kinetics and extract the rate coefficient. Let's start looking at a more complicated scenario. A plus 2B goes to D with C as a first order catalyst. I'm going to set up concentrations initially at 1 molar each. for each of the reactants and for the catalyst. So if we had this data going out further, you would notice that the plot looks really wonky. That's because, as is shown here, the data only goes up to 544 seconds. This is because I didn't want to make the spreadsheet even longer than it already was. This is going to change depending on the data that you're looking at, where that is, but you have to make sure that you are stopping short of that point, whatever it is. We can, however, increase the frequency of the data points if we want, up to our limit of 2,000 data points here. Okay, now let's analyze this system by the method of initial rates. We'll collect the data, add a new sheet to our analysis spreadsheet, and put the data in. X, comma, Y. Control C. Our new spreadsheet. Go to a new sheet and initial rates. Leaving some room. I will paste the data, remembering to paste values, time, and concentration of A. Now, doing the method of initial rates, one of the things we need to do is to keep track of the different concentrations for different sets of data. So we will put our initial concentration of A here. We'll put our initial concentration of B here. Let's try that again. F2 takes you into edit. Okay. And our initial concentration of C here. Going to add in an extra line here. And once we determine our initial rate, we will put our initial rate there, but we don't know it just yet. Shift end down, come back to the top, and let's insert our plot. If we look at just the early data, what we can do is double click on the axis numbers here. We can come on the right hand side under Format Axis to the one that looks like a bar chart. We can select Axis Options, and we can see how much we want to show. We only want the early time, so let's do something like that. And we see we have a bunch of data. It's not entirely clear how straight that data is going to be. Remember, what we want to get is the very earliest straight line that we can that is going to be tangent to the curve. If we only take, say, that first 10 seconds, I'm going to scroll down. I'm just going to go ahead and get rid of all of that data. You can actually see a little bit of curvature to it here. It's not very much, but it's present. So probably what we want to do is to take more data early on. So let's go back to our simulation spreadsheet, and let's say we're only going to take data for the first 10 seconds. And we're going to now take data every 0.05, something like that. So we've got a lot of data points, and they're really early, okay? Maybe even only go to like 2 seconds or something like that. Now that's looking pretty darn straight. What we're going to do is take this, XY, copy it over. We're going to switch back to this sheet, delete the data we had here before, and now paste in the values. You notice it went away. This is something about Excel. If you do something that makes the moving dashed boundary disappear, then that series of cells is no longer considered copied. So I'm going to come back here and do copy again, back over here, and we are going to paste the values. All right. Get rid of this. Select it. Insert chart. Whoops. We'll insert the chart here. And we will put in our trend line. We can see the trend line now. Trend line options will make it something visible. There we go. And that's looking pretty good. Yeah, that's probably looking pretty good. We'll call that one all right. As before, with the trend line selected, we come over, put the equation on the chart. I usually like to have a little bit more than 2 digits there, so we will go to number, make this say 5, and our initial rate is going to be 0.00879. Done with that one. Now, to do the method of initial rates, we need to start changing these. And you may remember it's convenient when to do this by having a simple multiple of one of the concentrations. So, come back over here. Let's double the concentration of A. We are going to now select X comma Y, copy, back to our analysis spreadsheet, and put it here. 2, 1, 1. Insert chart. Oops, I'm not in the right place. Insert chart. Trend line. Equation on chart. Number 0.01697. Call it that. Now let's do a comparison. Make a little more room. And a ratio. That divided by that. 1.93. So we double this, and this pretty much doubles as well. So that means that our order with respect to A is 1. All right. We're now going to do 1, 2, 1. So we're doubling B instead of doubling A. Okay. Now we take our data, X comma Y, Control C, over to where we want to paste values, insert chart, nope, trend line, select the trend line, look at it, oops. And I'm seeing more curvature in this one because this one's getting faster. So I think we need an even shorter period of time than we have here, because this is going to be underestimating what the slope's going to be. All right, so go down, get rid of that, come back over here. Let's only go out to 0.5 seconds, and we'll take data every 0.01 second. That looks a bit more straight. X comma Y, copy. We then paste values. Insert chart, scatter. Oh, I didn't put it up where we normally are, but that's all right. We'll go ahead and analyze it here. Trend line. Take a look at it. That's definitely looking better. We will put our equation on the sheet. We've got 3 significant digits. That's pretty good. So 0.0358. 0.0358. Now we'll take the ratio of this one to the first one. I unfortunately got an extra period and an equal sign in that expression. So it's about 4. So that means when we double B, we multiply the initial rate by 4. So this has to be second order in B. One more to do. Bring this over. We are now going to do 1, 1, 2 to double the amount of C. Coming back here. 1, 2. Let us take our initial data, x comma y, copy, over here, paste values. The region is selected, so insert chart scatter, trend line. Select the trend line so we can look at it. Looks pretty good. We're going to come over here, display equation on the chart. I typically like at least one more digit than that. So we now say that this is a number. Give myself some extra digits. 0.01798. Ratio this to this. Pretty much doubles. So we know that it is first order in C. We now have our rate law, which is going to be first order in A, second order in B, first order in C. We now need to determine the rate coefficient. Given that we now know the rate law, K, we can calculate the rate coefficient from any of these runs. So we take the rate divided by everything except the rate constant from the other side of the equation, divided by initial concentration of A times initial concentration of B squared times the initial concentration of C. Close our parentheses. We have our initial rate. Paste, paste, paste. Might as well average them to get as close as we can to the average value. We can say equals average of that one, and we can do control click to select the others. And we have 0.0088. Let's see how close we are. Back to our rate law, 0.0088. And so what you see here is that the assumption that we are getting the initial rates is a little worse than fitting an entire curve to the model. So what we get a rate constant that's of the right order of magnitude and is relatively close, but it's not bang on to it. Okay. Finally, we're going to do a quick run through to look at how to use the method of flooding. All right, to do the method of flooding, we're going to use the same expression, the same rate law that we had before. But we need to make one of the species here be a lot less concentrated than the others. And it needs to be the one that we are actually monitoring so that we can see it change. Now, the reason it looks scattered like this is we had the time set up so that we were only looking at the initial rates. So we now need to make this longer. We see that the data goes out to about 1,000 seconds. So let's just say 500 seconds. Too many data points. So let's do one every, say, 1 second. And we now have some data. Now, one thing to notice here is that this looks noisier. That's because the concentration of the species we're monitoring is extremely small compared to the noise value that we have over here. So to illustrate the method, I'm going to decrease our noise level so that we can see the data a bit more precisely. Okay, so we now have some data that we want to bring over. X comma Y, copy our new spreadsheet. I'm going to make a new one and call this flooding. Okay. I'm going to leave some room at the top to put more information in. So time concentration of A. Now we're going to have a column for the natural log of A. Equals ln of that. Copy. Paste. We are now going to select these, insert chart, scatter, and that looks pretty nicely straight. So let's label what we have. We have our initial concentration of A, our initial concentration of B, our initial concentration of C, and the pseudo first order rate constant that we end up finding from the data. Trend line, select the trend line, make sure we're looking okay. I'd say we look okay. Equation on the chart. Let's get some extra digits. And so let's see, 0.00111 and 0.009167. Don't know how many digits we're going to need. All right, get rid of that one. Now, back to our simulator, we need a different flooding value for B, 1.2. Okay, notice it's going faster. So the data out here tends to be noisier, so I'm just going to take maybe the first 300 data points that we're going to be looking at. So now, x comma y, copy, paste values, equals natural log of that, close parentheses, copy, paste. Oops, okay. Insert chart. Nicely straight. Add our trend line. Select a trend line. Equation on chart. I am going to give myself another digit. So our conditions were 1, 1.2, 1, and 0.0132. That's what we have on that one. All right. Let's do 2 more really quickly. We'll make this 1.4. X comma y, copy, paste values, equals natural log of that, copy, paste, insert scatter plot. All right, starting to get a little noisy down there. So the next one we're probably going to need to have an even shorter time frame than this, but this is probably going to be okay here. Whoops. Add a trend line. Select the trend line. Display equation. Increase our number of digits. We have now 1.4, 0.018014. Okay, we're going to do one more so that we have 4 data points to look at. Back to here, 1.6. All right, I'm going to only go out now to 200. Let's take the data a little more densely so we have more data points. So x comma y, copy, paste, copy, natural log of that, copy, paste, insert chart, trend line, select the trend line, equation on chart, okay, we have our values there. Now, what we're going to do now is plot our K observed versus our B zeros. So let's make K observed, concentration of B 0. So an easy thing you can do, actually I want these in the other order, K observed. So you can select this, copy, go here, and you want to go to paste special. We want to transpose it so it takes a row and turns it into a column. We want to do the same thing here, copy, paste special, transpose, there. And now we can plot our B naught, initial concentration of B, versus our rate and our rate constant. And we can tell, especially given that this, if it were a line, is not going to hit 0, right? 0's over here. This is almost certainly a quadratic. So we can test that by looking at the square root of the K observed. And that should give us a straight line if, in fact, it's second order. So we're going to say equals the square root, SQRT in Excel. Move over there. Copy, paste. And now we're going to select those, insert chart. And this is a straight line that definitely goes through 0. We're going to add our trend line. Yep, looks like a very nice straight line. So we now know that this is first order in B. I'm sorry, second order in B. We already determined it was first order in A because that's the one that's varying, and we got straight lines when we looked at the natural logarithm plot. To do the rest of the method of flooding, you would do exactly the same kind of thing we did here for C naught and figure out what the dependence of the pseudo first order rate constant is. So that is a detailed look at how to use this spreadsheet for simulating experiments, simulating experimental data, and how to use Excel in general to do the kinds of analyses that you're going to need to know how to do. So with this spreadsheet, you can go over to the rate law. You can put in pretty much any kind of mechanism that you're interested in. You can change up the frequency factor and the activation energy to get different rate coefficients that you might want to try. One thing I didn't go through here, but which is pretty straightforward, would be doing a temperature series. So you leave concentrations the same. You have the system set in a way where you know the reaction order already. But now you start changing the temperature, and you take the data over, and you can do an Arrhenius plot in order to find the activation energy and the pre-exponential factor. Feel free to play with this. Feel free to give me any kinds of questions on Piazza in class or in my office hours you may have about trying to use this. And let's get everybody proficient in analyzing kinetic data. Thank you very much.